Hello everyone, my name is Chinidhi Prakash. I'm a final year undergraduate pursuing my bachelor's in computer science and engineering at IIIT Vadodara International Campus, DU. Today, I'm here to demonstrate my project I have done during my summer internship at IIT Tirupati under Dr. Chalvadi Vishnu. So let's get started with it. So the main focus of our project is to perform semantic segmentation in self-driving vehicles and classifying and labeling different elements in the driving scenes to provide better understanding of the surroundings for the self-driving vehicle. To understand our project in a better way, so let us dive into some of the basics of this project, which are understanding the image classification and image segmentation. So when it comes to image classification, so it assigns a label to the entire image as a whole. So whenever you give an image, it identifies the object and gives a single label to the whole image. So like it will be classifying the cats or dogs or something. So the entire image is getting a label. When it comes to image segmentation, it is somewhat a different. So the image is separated into different regions or segments. So each pixel is given a label. So it is like whenever you give a picture of a cat, suppose let's say it is in a ground or something. So it identifies each pixel and gives each pixel a label. So it gives the labels to the pixels which contains the cat image. Next, it contains the background. Next, sky. So it gives labels to each and every pixel and segments the image into different regions. So this is the main difference between image classification and image segmentation. Now let's see some of the image segmentation techniques. So some of the image segmentation techniques are thresholding and edge-based detection. So when it comes to thresholding, the original image is converted into grayscale image and the threshold value is fixed. Let's say if the pixels intensity is greater than the threshold value, it will be mapped to one value, like let's say 255. Otherwise, if it is less than the threshold value, it will be mapped to the zero. In this way, a threshold value is fixed and the image is segmented into two parts. Now, when it comes to edge-based detection, so the sharp edges between the regions are in objects are detected and the segmentation is done. So in thresholding, a fixed threshold value is maintained and checked whether the intensity is high or low, and this based on that value it is decided. In edge-based detection, the sharp edges between the objects or instances is detected, so that is known as edge-based detection. These are some of the image segmentation techniques. You can see the some of the images I have done here. So now let's dive into the main part of our project. So our main focus is to perform semantic segmentation in self-driving vehicles using unit architecture model. So let's discuss about the data set. So in our data set, we have 5 different types of images data. So we are considering 500 images from each type. Now that will be of 2500 images. Now we are labeling 13 types of classes and we are giving the data as batches. No, so the size of the batch will be 32. As we are considering RGB images, the number of channels in each image will be 3, and we are dividing the data set into 80% training and 20% testing. So this is all about the data set we have used. Let's discuss about the model architecture of unit. So the unit model contains an input image, some encoders, a bottleneck, decoders, and skip connections, and the output image. So first of all, when it comes to input image, it is the initial image which we want to perform segmentation. Encoders are used to extract the features and downsample the input image. And the bottleneck is like compressing the image into main features, and it acts as a bridge between the encoders and decoders. Now, when it comes to decoders, so the image is downsampled through encoder side. So it is reconstructed and upsampled through decoders. And skip connections are like transferring the main features from encoders to decoders. So This is the use of skip connections, and the output image is the required segmented result. Let's discuss about the procedure. So now here are the main steps involved in this project. So I would like to explain these steps in detail through code. So let's dive into the code. Now let's discuss about the code. Firstly, we'll be importing the necessary libraries. Next, we'll be declaring some variables like height, width, channels like RGB, number of channels 3, and number of classes as 13, and we're declaring batch size as 32. And now we are preparing the data set. We'll be giving the source directory, and the path is given to the source directory. And we'll be taking two empty lists like input image names and mask names. And as we discussed, there will be 5 different types of image data. Now we'll be iterating those 5 types of data and taking some random things, and we'll be inserting into input those input image names and mask names randomly. And this part is used to divide the like splitting the data set into training part and the testing part. 80% is provided to training the data set. This function is used to convert our 2D image into 3D array. The third dimension will be the channel which it belongs to. Okay, the class which it belongs to. The third channel tells us that which label does it belong to, which class does it belong to. And this part is used to give the color to the segmented image. And we are just taking some random images and we are observing them. This is the original image, this is the mask, and this is the masked image, which is the combination of original image and the mask. And this is the data generator class. It is used to load and process the different types of images and masks for the training. And it is the initialization function. So it will be taking image file names and mask file names. Those paths are included with them, and we'll be converting them as as a tuple. Those image file names and mask file names as a tuple, and we'll be providing the batch size where we provided as 32 above. And this function, like, it is called whenever an epoch is completed. So it will bring shuffling to to provide regularization. And this get data, it loads and process the batches of images and masks. Here it is reading the image file and resizing each and every image so that all will be in uniform size. All input images will be of uniform size. And we are dividing the image with 255 because we'll be limiting those intensity values between 0 to 1, and we'll be returning the images and segmented images as arrays. And this get item part is used, uh, and we provide an index, it will be providing a batch that corresponding to the index. That batch is provided to us as a return, and it is obviously returns the length. Here we are giving the training and validation. We are providing those training images and masks to the data generator. Here validation images and masks are provided, and this is about the shape. And here is like it is the original image and it is the mask. It is taken as random. And this is the definition of the unit. It is the first of all input, and it contains encoding layers. Encoding is used to downsample the image to extract features. The encoding layers contains convolutional layer and a leaky activation function, and normalization is done and repeat. And between the encoding layers, a max pooling layer is introduced, and the same encoders are repeated. And when it comes to decoding layers, it is used to upsample the image to reconstruct it. So upsampling is done, same convolutional layers, Likerelu, normalization, repeat, and upsampling. So this is all about decoders and encoders in the unit architecture. And this is a summary of it. And it is a figure describing the same. And here we are defining the learning rate manually. Here we using the Adam optimizer and the sparse categorical cross entropy loss function. And our main metrics is the accuracy. Here we are learning rate callbacks. we have some checkpoints and we are saving the best values. And it is the history of the training, for each and every epoch, the validation loss is calculated whether it is improved or not. And these are the results, like we have achieved an accuracy of 0.94. Blue one is the training accuracy and the orange is the validation accuracy. Both are at most equal at max. And the same with the training loss. We have achieved an training loss of around 0.14. Both the training and validation accuracy, as the epochs are moved, they converged, which is a better performance. And we are saving the weights and loading into the model. And now we'll be performing testing. So for the data generator, we'll be performing testing now. And after testing, this is the output. This is the original image. This is our predicted. So it is predicted by our model, and it is the ground truth. So almost they are similar with, that's why we have achieved an accuracy of 0.94, that is 94%. So almost it is equal. And these are the outputs. So this is all about the project and the code we have performed. So I'll be providing this GitHub link and the other resources I have used. And this is all about the project. And thank you.